We're good to go? Okay. Hi, everybody. My name is Sebastien. I'm working for Intel, and I'm here to give you a few hints about how Kata Containers actually works. So let's get started. I think and I know, actually, that you all love containers, and you use them every day. But the question is, do you really know how a container works? So I'm going to give you a quick container 101. A container is basically how you isolate processes from your host. And the idea is that the process can be isolated by namespaces and C groups. So namespaces like PID or network, the way it works, your process is going to run on its own, and it won't be able to see other process PIDs. The same way with the network, you have a bunch of interfaces on your host kernel, on your host, and what happens is that if you run your process inside this network namespace, then you won't see those interfaces. Different way to isolate them is actually to constrain your processes based on CPU, memory, network constraints. You can make sure that your processes will only use one CPU and a certain amount of RAM. So basically, that's how containers work. Problem with that is that software is not really secure. So when I say software, I consider that the isolation comes from the host Linux kernel. And this is not enough, because if you think about a container process being malicious and trying to exploit your kernel and actually succeeding, then it can exploit other containers running on the same system, or more simply, it could just crash the kernel, meaning the denial service for all your other container on the same host. Well, to solve this issue in production, what people do, they actually run this inside VMs, but they have to manage their own VM, and that means that they have to deal with painful management. That's why 2 years ago, Hyper.sh and Intel came with similar ideas of how to run containers inside virtual machines, but seamlessly integrated with the whole ecosystem. And so this was the idea 2 years ago. We made our way, and eventually 6 months ago, we announced Kata Containers as being the merge of those two projects. How Kata Containers works? Well, that's fairly easy. Instead of relying on software isolation provided by the kernel, instead we rely on hardware virtualization, which is a stronger isolation. And we run each container inside its own VM, meaning that it has its own guest kernel. The benefit of this, even if your malicious container process can make it through the guest kernel, then it will just crash himself, and it will not harm other containers running on the same host, because it will never make it through the VM isolation that you can see on the picture. Now, a little bit about cloud ecosystem. The idea behind Kata Containers is to be seamlessly integrated. Otherwise, it would be hard, actually, for users to leverage Kata Containers. And I will show you how we're integrating into the stack. Well, if you look at OpenStack, it calls into Docker, and eventually will call into a layer a standard that is called OCI. And runC is the standard container runtime that will spawn your container on the orchestration layer behalf. Same way with Kubernetes. It will call into the CRI layer. This CRI layer will be translated into OCI calls by implementation like CRI-O or CRI containerd. And again, runC will be the one running your container. Well, because OCI is the common part between those two different stacks, we have simply replaced it with Kata runtime. And you can see here that this is a container, but running again inside its own virtual machine with its own guest kernel. Now, a little bit about architecture details. Kata container is, I would say, four main components. The runtime, the shim, the proxy, and the agent. The runtime will be the one called every time you have an OCI command being triggered, which means that the orchestration layer eventually will end up doing a Kata, a runtime run my container. The runtime will be called, and will try to communicate with the agent inside the VM. The agent being responsible for actually spawning your real containers, because the real processes are running inside the VM. But now your orchestration layer doesn't know anything about those processes inside the VM. And for that reason, we need a shim, which is the representation of your container on the host side. The proxy is in different color because the proxy is optional depending on your host system. In particular, depending on your kernel version, if you are on a 4.8 or plus, this is great. You won't need the proxy. Otherwise, you will, because 4.8 introduced the support for vsock. And on older kernels, your VM will use vert.io serial to actually make the communication between the proxy and the agent. And the proxy, because that's a serial connection, well, it will just multiplex all the connection with different shims and runtime to the agent. Now, I've been talking about how we can simplify this architecture. We have just removed the proxy here, and instead we rely on vert.io vsock, meaning that we have a real socket communication, and this is we don't need an actual component to handle the multiplexing and demultiplexing between communication. Now, let's dive a little bit on the OCI lifecycle and how Kata handled that. So when your orchestration layer calls into the runtime during Kata runtime run my container, well, the runtime first will start your VM, and the guest kernel will boot. Then the agent is going to be started, listening to this serial. I'm taking the case where your kernel might be 4.4. From there, the proxy will be started, and then it will just connect to the VM. When the connection is actually established, well, the runtime will be able to communicate directly with the agent, and on its behalf, the agent will spawn the container. So you can see the process being isolated by a namespace, a set of namespaces here. And to represent this process on the outside world, on the host, actually, the shim will be started, and will handle all the communication so that the orchestration layer will receive all the std out and stdr that you would actually expect from a regular container. You can see that the runtime is not here anymore because the runtime is a short-living process. It's just here to configure and start things, and then it can just terminate and return. Same thing with exec. That's a quick example. The exec means that we're going to talk to the agent, and inside the same set of the same set of namespaces, we will spawn another process being a child of the container process. And again, we need another shim, and that's it. So I've been talking a lot about OCI, but Kata Containers is more than OCI. OCI is one way to be integrated into the whole ecosystem. But as you can see, like 90% of what Kata Container is actually this package and this API called vert containers. And here are implemented almost all the features that we have. So multi-hypervisor support, which is in scope, because right now we have only QEMU KVM. For the network, we support several plugins, CNM, CNI, and we have several ways to actually connect the network between the VM and the host. We'll see later how we handle devices and storage, but that's the idea. Like you have this whole API, and you just need some wrapper like Kata runtime to handle the OCI layer, or like Fracti doing the direct translation between the serial layer and Kata. And those are the way you can actually expose this Kata API. So let's now dive a little bit into technical details. So first, the OCI compatibility. OCI is a spec which is not that large, but now if you look at runC, I was talking about runC, which is the standard container runtime. runC defines a bunch of different things, and to catch up with what's defined by runC, well, we did one thing very simple. We have our agent leveraging libcontainer. Libcontainer is the core of runC. It's like Kata API with Kata runtime. That's the same. Like, this is really what runC is, runC being just some sort of wrapper. And leveraging libcontainer, well, most of what we have to do is handled already by libcontainer. So we have some sort of mini runC running inside the VM itself. Now, I've been talking a lot about Kata containers and how containers are great, but to keep those Kata containers great, we need them to be fast and lightweight. And the way we actually achieve this is to leverage different features like NVDIM, which allows us to share the same VM rootfs on the host, meaning that we're reducing the memory footprint, we don't duplicate things. DAX is another way. So your guest page cache is completely disabled. You're not copying things into the guest kernel, and that's a second way to reduce the footprint from a host perspective. A third way of reducing this memory footprint is to use KSM. So we kick the KSM daemon on the host to every time we start a container, saying, just look at all the pages that are marked mergeable and try to find if there's identical pages. If there is, KSM will just merge them for you, reducing, again, the memory footprint of your system. Now, I've been talking about lightweight VM. We need those VM to be fast and to boot fast. This is something that is actually pending, work in progress, but that is pretty cool. We rely on a VM RAM snapshot, and we start our VMs from there, meaning that you will not have to boot the kernel from scratch. You already have your whole RAM being provisioned, and from there you can just start your container. So that's one way to go fast, but this will also allow to reduce the memory footprint because all your VM will share the same RAM content on the beginning. There's one drawback, and that's why this is not enabled by default. The drawback is we need to figure out how to provide a proper entropy, because having the same RAM content actually introduce some security issues. So we have to figure this out, and that's why it's in progress. Another way to boot fast is to start a tiny, what we call a tiny VM, meaning that we start a VM with only one vCPU and 128 meg of RAM. That's the minimal amount of resources that you need to run a basic workload. If you need more, you can still ask for more, and this is going to be a hot plug later. So while your VM is being booted, we can prepare things like preparing devices, and when the VM gets ready, we can just hot plug those extra vCPUs that your container need, and those devices that we need to pass inside the VM. And that's how we parallelize things and the way we actually increase the performance. So devices. When you don't have devices on your hardware, but you still want to pass devices to your VM, well, you rely on emulation. And vert.io is the standard to do that. So basically, you have your guest kernel with, I took the example of vert.io SCSI, which is a block device driver. Vert.io SCSI front end on your guest kernel is going to call back into the host kernel. So is going through vert.io SCSI backend using MMIO. And eventually, it will go through the user space process that QEMU is running and will emulate your block device. So that's great because you don't have devices, but you can actually pass devices to your VM. Now the drawback is performance. And big performance problem with actually doing the emulation in the user space. That's why one improvement is to rely on emulation being done inside the kernel, so no context switch in this case, but this is still emulation. But that's a first improvement. Now, how to really be closer to what you can expect from bare metal performance? Well, you go with PCI pass-through. So let's say you have NIC hardware in your system. Well, the only thing you got to do is to unbind this from the host kernel driver and to rebind it to a VFIO PCI so that you can provide this hardware directly to your VM. Now, this is great, and you can actually be very close to what you can expect with bare metal performance. But there's one thing, only one VM can be attached to this NIC. So now on your system, if you want to run 100 containers, and in this case VMs, you will have to be able to provide 100 NICs, which might be very expensive. And that's why SROV is super interesting, because this NIC, if it's SROV capable, which is a hardware feature, it will be able to expose several virtual functions. Let's say this NIC is capable of exposing 64 virtual functions, then you could run 64 different VMs, seeing those virtual functions as distinct devices. And that's another way to be scalable and to still achieve good performance. Now, a bit of background about how we handle the network. So I've been talking about those namespaces inside the VM, isolating our container process. But there's one namespace that we need to run on the host, and that's the network namespace. The reason for that is that network plugins expect to create an interface between the container network namespace and the host network namespace. The host network namespace. And that's why we need to provide this. So when you run a container, first thing, we create this network namespace. We run the VM inside. And now that our VM is running, we need a way to connect it to the outside world. And MacVTAP is the choice that we made to connect this VETH pair that has been created by your CNM plugin, for instance, with the VM. MacVTAP is preferred here to what could also be done with a Linux bridge and a tap interface, because it actually removes one layer, which is the Linux bridge. So it's more performant. TC mirroring, or traffic control, is another way to handle the network between the VM and the outside, the host namespace. So the question is, why TC instead of MacVTAP? Well, the answer is TC could also handle layer 3 networking, because it will just take, you just define some rules, you take some packets there, and you push them to the tap interface, and the other way around, you take the packets from the tap and you push them to the VETH pair, or any, in this case, this would not be a VETH, but let's say that you're using a CNI plugin, which is IPVLAN. Well, this is a layer 3, and MacVTAP will not be able to connect to this interface. And that's why TC mirroring is in scope, so not developed yet, but this is something that we want to handle more use cases than MacVTAP could do. Storage. So what you can see here on the host file system is basically your container rootfs. So when you have your Docker image and you expect to see a Ubuntu inside your container, then you actually provide a rootfs. This rootfs, depending on the storage driver that you're using, like overlay, will provide you a file system on the host, and you need to pass this inside your VM. So the way we pass that, we rely on Virtio on 9pfs, and Virtio 9p is the emulation driver for that. Now, 9p is working, but is not super performant. And second drawback is that it's not completely POSIX compliant. So we have some issues related to this. And that's why the preferred way that if you actually want to run Kata container in production would be to rely on a storage driver like device mapper, providing your rootfs as a block device. And in this case, we can hot plug this block device through the VM, exposing your rootfs directly to your container, but this would be way better performance-wise. Now, some more detail about host namespaces. I've been already talking about network namespace, and how we actually run the VM inside. But the network namespace, so you have your orchestration layer, and it needs to understand which is the network namespace associated with your container. And that's why we also need to run the shim, which is the container equivalent on the host, inside this network namespace, so that it can determine what is the network namespace your container is running into. The PID namespace is a different explanation. You have let's say that the yellow one is your container process, and you spawn, you exec, so you spawn a child of this container process. Well, you don't want the child to stay alive if your actual init container process terminates. And that's why on the host, we just put all processes related to one container inside the same PID namespace. Because when this shim will die, when this container will die, then all the other child will be directly killed by the kernel, because that's one feature of the PID namespace provided by the host kernel. So we've been talking a lot about sweet things about Kata and how we can match the OCI spec, but and we're just trying all the time to catch up with what's runC doing. But there's one thing we're doing actually better than runC, and that's the multi-OS support. Because runC container or standard container are running on the same host, well, if your host kernel is not capable of handling specific hardware because it doesn't have the drivers that you need, well, you won't be able to run containers leveraging this hardware. In our case, you don't really care about your host. You just need to provide a specific guest kernel and say that I want to run my Kata containers with this kernel. This way, you will be able to leverage a specific GPU, and you will be able to access it from inside the VM. So that's pretty sweet about Kata, because that's a differentiator from runC. So time to wrap up. I would like you to just remember 3 things about Kata. This is secure, way more secure than just runC containers we run on the host, because we're leveraging hardware isolation, where runC just leverage software isolation provided by your kernel. Kata containers are fast and lightweight, not as much as standard container, but we're trying to be as much as we can. And Kata containers are easy to use. So if this guy can do it, I think you can do it. And the idea is that we rely on this OCI layer. I've been talking about the whole presentation, and that's really the point on how to be seamlessly integrated with the whole ecosystem. And that's the point of Kata containers. We don't want you to be spending like a day trying to run Kata containers. So the only thing that's remaining is for me to ask you to just use it, play with it, and contribute if you can. find some bugs, because I'm sure there's some. Talk with us on different medium like Slack, IRC, on our mailing list, and go today to the booth. There's the Intel booth where you'll be able to see some nice demo about how Kata containers work. And please go to the other session, especially at 2 p.m. There's a nice demo about Kata container. Eric will try to demonstrate how you can deploy very fast Kata containers in a Kubernetes environment. So just go to the session and enjoy. Thank you. Yep.
Yeah, hi. I'm just trying to understand the memory consumption model for runC versus Kata. So if I say spin up a runC container with, let's say, 2 GB RAM, I know that I would get 2 GB RAM. But here you're spinning up a guest kernel, and then you're spinning up a container inside the guest kernel. Mm-hmm. So the 2 GB is for the entire guest kernel plus the container, or how is it there? I'm just unclear a bit there.
So you're starting a runC container saying that you want to run, you want to constrain this to 2 GB of RAM, right?
Yeah, that's
well, we also apply C groups inside the VM, but we need to run this VM to be capable of providing you 2 GB of RAM. So we run the VM with at least 2 GB of RAM, and inside we also pin the process to be constrained by C groups.
Okay, so a runC container versus Kata container is, if you say a 2 GB runC container, you would consume a 2 GB of host physical memory. Mm-hmm. But if you say a Kata containers container, it's a 2 GB container plus the guest kernel's memory plus the user space.
Yes.
Included.
Yeah.
It's like that, right?
Yeah, exactly.
Okay. Yeah, thank you.
So Google announced the Gvisor, which is very similar to the Katas. And how do you compare the Gvisor with Kata?
So Gvisor and Kata are different projects. I mean, there's overlap, obviously, but they target different workloads. Let's say that you don't have a lot of I/O and syscall. If there's not heavy syscalls being involved in your workload, then you might prefer to run Gvisor. But if you want higher security and if you have a lot of I/O being handled inside your container, then you might prefer to use Kata instead. So I think it really depends on the workload that you're going to run. Yeah. DPDK? Can you repeat the question? Yeah, so you ask what happens with DPDK in this case? Well, we can handle the DPDK scenario by passing the driver inside the by passing the device inside the VM, and then you just use something like VFIO inside the VM to run DPDK.
You can run it inside and into. So you can use VM's user to get DPDK into the VM, and then you can run DPDK inside the VM if you want. That works today.
You can, okay, go ahead. Yeah, so it leverages VOS chooser. So you can run this inside the VM, and that's it. Sorry, I can't hear. Okay.
Hello, it's very interesting. And we are usually creating Kubernetes cluster based on VM, Nova VM, using libvirt driver. And actually, can we, it's just a personal question, can we use Kata container on virtual machine as well?
Yes, so it supports nested virtualization. Actually, our CI runs in Azure, so it runs inside VMs. And yeah, you can just use it as is.
Thank you.
So I understand that the container is running on top of VM and not on top of a host.
Mm-hmm.
So what is the meaning of privilege mode when you're running the container? Because when you work with privilege mode, you can have access to the kernel of the host.
Exactly. So that's why we
now.
Yeah. So that's a limitation, a current limitation of Kata. Like if you ask for a privileged container, then we'll run for you a runC container, because when you run privilege, you expect to be able to access the host network, and for that reason, you have to. We have to provide you a runC container, because Kata doesn't fit into the privilege model.
I think that's like today, that's how it is. I think in general, privileged isn't as dangerous if you're using Kata. So we cannot do host networking. That's not going to be supported. But if you want to do privileged because you want to hack on the kernel, do different things, privileged isn't as sketchy and scary in a Kata containers context. So we're kind of looking at what does it mean? Could we support privileged in a subset of features to be able to allow you to modify the host kernel and do all these things, like a Kata privileged. But I think reusing the same privilege flag makes sense. It's just we have to figure out, and maybe people have input on, how do we handle, hey, you can't do host networking. You can give it privileged. It's safer, but, it's not exactly the same privilege that you would expect in a namespace.
Okay. Thanks.
Given the last question, I'm interested to know what the advantages of running it as a container in the VM rather than just running a super lightweight VM that uses the rootfs of the container.
Sorry, I didn't get the question.
So you spin up the container, the VM,
Yeah.
and then you run a container inside the VM.
Yes.
Why can't you just run a VM using the rootfs of the container?
Well, what? Yeah. So that's the context of a pod. So with Kubernetes, you have the concept of pod. That means that you can run several containers on the same host, and we still want the container isolation between those containers. Well, so a pod is supposed to run containers from the same user, so there shouldn't be malicious between them, but we still want to run them inside namespaces. We don't want those processes to run next to the agent, and that's also one of the reasons that we still run those processes inside namespaces, inside the VM. Okay, no more questions? Thank you.